65 million years ago, a rock the size of a mountain smashed into the Earth. Back then, the world was ruled by the dinosaurs, until that catastrophic event wiped them out. But how could that collision, near to what we now call Mexico, kill creatures half a world away on the remote Pacific islands of New Zealand? What really happened to the dinosaurs? New Zealand's ancient Maori name is Aotearoa, land of the long white cloud. For millions of years, its misty valleys have guarded the secret that dinosaurs once lived here. Even 25 years ago, most scientists were convinced that dinosaurs had never reached these remote islands, where the oldest reptile was thought to be the prehistoric tuatara. But that was before a remarkable 80-year-old housewife and self-educated paleontologist Joan Wiffen went exploring in some rugged backcountry and found New Zealand's first dinosaur bone. In 1975, Joan and her late husband Pont were working a small stream in the Tahoe Valley on the east coast of New Zealand's North Island. They had just taken up fossil hunting as a hobby, and, late one summer's afternoon, they found a strangely shaped bone, which experts later determined was a vertebrae from the tail of a theropod, a meat-eating dinosaur, possibly a megalosaur. This creature stood on its hind legs and had sharp claws to catch its prey. Air pockets in its skull made the theropod's head light and agile, and its teeth had serrated edges to tear the raw flesh from its prey. Joan had found a killer. But where were its victims? Since that first historic discovery, Joan's been on a mission to recover all of New Zealand's lost dinosaurs. A mission that keeps bringing her back to the Monongahela stream, where her adventure began. It's tough going, with stonecutter, hammer and chisels in your backpack. Everything has to be carried along narrow bush tracks. One slip could mean a nasty tumble into the icy stream far below. Joan's dedicated team of fossil hunters have lost count of how many times they've roped themselves up and down to this narrow mountain stream, bringing in heavy equipment or lifting out huge sandstone rocks with their treasure trove of fossils locked inside.
Still there, Joan?
Yes.
Last time they spotted a couple of promising rocks, and today they want to work on them.
Oh, look, Trev, it's...
The Monongahela stream often floods and can shift even large boulders a long way downstream. But, good news, the stones they need are still where they left them. First priority is to recover a marine fossil on the other side of the stream. So, 74-year-old Trevor Crabtree and fossil hunter Robin Adams brave the icy water to get to it. For Joan, the Monongahela is a magical place, with its moss-covered rocks rich in fossils. In fact, it was a casual comment about the existence of reptilian fossils written on an old geological map that drew her to this spot. She remembers, as if it were yesterday, the first time she saw the stream.
We were following some instructions we'd read on this particular map, where it It's said in the small print, of course, that in the Martyr series, and that's the age of these particular rocks, that in the brackish waters of the Tihoi Valley, reptilian remains had been found.
You mate, is that right?
Yep, should be right.
When we first went down into this site and found huge numbers of fossils, we realised that most of the fossils at this site are found in concretions. Now, concretions are usually round, oval, pear-shaped rocks, and they range in size, anything from the size of roughly a golf ball to great boulders which may be 2.5 metres in diameter. So there's quite a variation. Sometimes the fossils are exposed on the outside, but in most cases they're in the centre, caught up in these ripples and behind these rocks.
And wrapped up and sealed inside these concretions are the fossils. Rock-hard time capsules created 65 million years ago, when the Monongahawanga stream was a very different place. When the dinosaurs ruled this part of New Zealand, it hadn't yet been pushed very far up out of the sea. So the low-lying Monongahawanga wasn't a mountain stream, but a broad, shallow river that emptied into a sandy bay. The final resting place for an ailing theropod who collapsed here and died. Scavengers tore the flesh from the dinosaur, and bacteria reduced its remains to a skeleton. When the bones crumbled and fell apart, the next flood tide swept them towards the sea. In the shallows, the bones sank into the mud, and, in the process called concretion, limestone particles bonded onto it, finishing up as a smooth oval rock. Much later, huge earthquakes pushed this land up out of the sea and brought the fossil-bearing rock to the surface in Joan's favourite stream.
Well, here's a good example. This, as I say, is a concretion, and this particular one is quite valuable because here you can actually see the exposed fossil. In this case, it's actually a vertebra.
To win the fossil from a rock, you must first cut away the excess sandstone with a power saw. Trevor lubricates the blade to keep the dust down, while Robin makes his incision. It's tough, back-breaking work, but they've done this many times before. And it used to be a lot harder to extract the specimens in the early days, until Joan and her late husband Pont saved up enough money to buy their first stone saw. At first, the Wiffens were mainly finding the bones of ancient marine creatures that once lived in the seas around New Zealand. Like this fragmented skull of a mosasaur, one of the largest and most voracious predators ever to hunt in the South Pacific. The mosasaur is thought to have descended from an ancient species of giant monitor lizard that gave up hunting on land and went back to the sea. Over millions of years, it lost the ability to walk, and its feet and legs became huge paddles to steer its massive, eel-like body through the water. A skull Joan found was 75 centimetres long, the length of a man's arm, with razor-sharp teeth and a hinged jaw which allowed it to swallow very large prey. These air-breathing reptiles could grow to 12 metres, almost 40 feet in length. They were perfectly designed killers from the day they were born, live from their mother's belly. Robin and Trevor think they may have found another mosasaur bone, but they won't be sure until they get it back to home base. And Trevor knows that won't be easy.
Well, I have to tell you the old measure because I can't remember what the new one is. But the old measure, 1 cubic foot weighs 100 weight, 112 pounds. Now you can imagine putting 112 pound on your back, and you saw where we came down. We're going to go back up there with that. That's 112 pound. From the bottom up. Wah! We couldn't have done better. We've lost a ½ an inch of bone off an eroded limb bone. We've lost nothing.
Successful finds like this have kept the team motivated over the years. For there is certainly something very special about recovering the remains of a creature that died more than 70 million years ago. What were they like, these giant predators? How did they move? What did they eat? The truth is, we know very little about mosasaurs. But with their huge jaws and sharp teeth, they could easily have devoured the largest of fish, then or now. One delicacy the mosasaur might have enjoyed were these enormous ammonites, thought to be an ancient ancestor of the squid, which back then had a hard shell to protect its soft body. These ones grew to the size of a tractor wheel. But even the toughest shell was no match for the powerful jaws of a hungry mosasaur. A distant relative of the mosasaur survives today. The Komodo dragon, the world's largest living lizard, still rules the island sanctuary of Komodo in Indonesia, where it has lived for the last 150 million years. While a Komodo dragon may look like a dinosaur, it certainly isn't. For a start, Komodos are cold-blooded reptiles, whereas most, if not all, dinosaurs are thought to have been warm-blooded creatures that walked on straight legs tucked directly underneath their body. This adaptation allowed them to move much faster than reptiles like the Komodo dragon, who look as if they are doing continual press-ups on legs that splay out at right angles from their bodies. As the moon rises over the Monga Valley, Joan retreats to her hut to prepare some of her fossils. In this too, she has been a pioneer, because 30 years ago, when she started, no one in New Zealand knew how to do the acid extraction method, in which a specimen is soaked in dilute acetic acid to eat away the sandstone, but not the bone. With patience and determination, Joan has perfected a technique which has allowed her to recover the bones of many ancient creatures. Among them was a bone from the wing of a pterosaur, a flying reptile that once hunted for fish along the New Zealand shores. But one of her favourite discoveries were the fossil remains of an elasmosaur, the long-necked creature of Loch Ness Monster fame. One of the most successful predators ever to hunt the world's oceans. Joan recalls how a very valuable elasmosaur skull was discovered with the help of a stick of gelignite.
My husband and a cousin were going upstream with some of their explosives, looking for some of these specimens that we couldn't get out of holes and we couldn't break with hammers and chisels. So this specimen became apparent in the creek after a loud explosion and a plume of water flying in the air, and then we sort of rallied round to pick up the pieces, and this particular specimen I think was, from memory, in about 12 or 14 pieces, and I collected up this assortment of rocks, and slowly and painfully extracted it piece by piece. Actually, it turned out just like the picture books, because I'd been very doubtful about these extraordinary-looking teeth that looked as though the animal required some attention from an orthodontist, but in actual fact, that's just the way they were. So this has become quite a well-known and quite a valuable specimen.
No complete elasmosaur skeleton has ever been found in New Zealand. But in the Denver Museum of Nature and Science in Colorado, visitors can gaze up at a superb specimen hanging in the entrance hall. It reaches up for almost 3 complete stories of the building. The museum's resident elasmosaur expert is Walking with Dinosaurs consultant Dr. Kenneth Carpenter.
Elasmosaurs lived about 65 to 100 million years ago, and they lived in the ocean worldwide. They've been found in England and New Zealand, as well as here in Colorado. The interesting thing about this group is that they have a very long neck and a very small head. This head here is about 30 centimeters long, and the body, though, is 10 meters. So we're looking at a ratio of actually 1/30 of the body size, so it's small. They have a very large body. I could probably easily stand up in its rib cage. What we do know about elasmosaurs, which we've tried to convey in the way this skeleton is displayed, is that the eyes kind of face upwards. So they probably swam in the deeper part of the water and watched for schools of fish swimming above. And the schools of fish would stand out against the blue of the sky. And so all they had to do is just carefully, quietly come up underneath and grab the fish and swallow them whole. That's probably their main lifestyle, and they were very successful at it, surviving for over 40 million years.
Visit the central North Island of New Zealand today, and it isn't hard to imagine what this part of the world might have looked like in the months immediately prior to the asteroid impact 65 million years ago. New Zealand was much closer to the South Pole back then, but it can't have been particularly cold, because in 1994, Joan found part of the rib of a sauropod, a dinosaur which has only been found in warmer climates. These huge, plodding creatures were vegetarian, so they must have frequently been on the move, searching for tasty plants. And they needed to eat a lot of them. In New Zealand, sauropods could grow 12 meters or 40 feet long. But all creatures, no matter how big and strong, eventually die. And when a sauropod became sick or injured, it provided a welcome meal for any scavenging theropod, which happened to be lying in wait. Theropod is the name given to all two-legged, meat-eating dinosaurs, and, like this megalosaur, they all had razor-sharp claws and teeth. Joan vividly recalls that day when she found the precious bit of a theropod's tail, which proved that these carnivorous dinosaurs had once lived in New Zealand.
So I picked up all the pieces of rock, or 2 or 3 little bits of rock, and took them home and went through this acid process to extract it. And I found this rather strange little vertebra. We took photographs and measurements, and I made a cast and sent it over to Dr. Molnar at the Queensland Museum. And about 10 days later, I got a phone call, and he said, "You've got a dinosaur."
But as important as Joan's find was, one bone simply isn't enough for the experts to determine exactly what kind of two-legged meat-eater lived in New Zealand. However, this Allosaurus skeleton would have been similar in size, shape and behaviour to the New Zealand theropod.
We know that this was a meat eater because if we look at the teeth, they're very long, slender objects, much like the steak knife. You can even see it's pointed on the top for piercing. Along the back and front edges are these little serrations so that it can cut through the hide and into the muscle. In this case, probably ripped out large chunks of flesh. And we know that these were active hunters because if we look at the claws on the hands, they got these huge hooks that could grab and dig into the prey while the head come down and just rip the flesh right out. That's probably how it killed its prey.
So what animals were on the New Zealand theropods menu? One possibility were these small plant-eating dinosaurs called hypsilophodonts. Theropods probably had a great sense of smell and may have sniffed their prey long before actually seeing it. But the hypsilophodonts had the advantage of speed. They were the gazelles of their day, fast, nervous, always on the alert. So the slower-moving theropod would probably have had to ambush a herd to stand any chance of catching one of them. But how do we know that theropods were hunters as well as scavengers? Was, say, a megalosaur really fast enough to catch its prey? That's the puzzle Cambridge scientist Dr. Julia Day has been trying to solve. At Ardley Quarry in England, theropod footprints have been discovered embedded in ancient sediments. By studying the position and distance of these megalosaur prints, Dr. Day has been able to reach some conclusions about whether these creatures could actually hunt or not. Her findings suggest that theropods like the megalosaur were, in fact, able to hunt down smaller, faster prey.
In the summer of 2000, we came down to Ardley Quarry to rediscover the sauropod and theropod trackways, which one of the quarry workers at Ardley had found 5 years previous. And unfortunately, as we see today, these tracks are covered in, and that's basically because it's a working quarry. But we actually made some of the casts of these trackways, so we can see those at the Oxford Museum.
In 1824, Oxford Museum housed probably the first dinosaur fossil, when pioneer paleontologist William Buckland identified a jawbone as coming from a megalosaur, meaning the great lizard. At the time, the exhibit caused a sensation, and in its day was as popular with the public as the set of footprints taken at Ardley Quarry by Dr. Day are now, set into the lawn outside the main entrance.
Now, this is one of the casts of the theropod trackways that we saw at Ardley Quarry. Now, these theropods came from the Middle Jurassic period, and that's about 163 million years ago. As you can see from the size of the footprint, these animals are pretty large. They're probably about 9 metres in length. This footprint's about 70 centimetres. And as we can see from this footprint, it's a theropod as it's got 3 toes, and there's claw marks at the end of each of the toes. Now, when the animal was running, the speed actually increases from about 5 kilometres an hour to about 30 kilometres an hour. So we've got a massive increase in speed from walking to running. Before this discovery, we only knew that the small theropod dinosaurs could run, and we didn't know that the large theropods, that is, dinosaurs similar to T-Rex or Allosaurus, could actually run. We know from the trackway evidence that this animal could run for at least a short period of time. So this animal actually probably was an active predator. That means it actually was chasing its prey. Now, what we don't know, or the unanswered question of this research, is for how long it could sustain its run for. Was it a sprinter or was it a long-distance runner?
So a theropod may have been able to catch a hypsilophodont. But it wasn't until February of 1987 that Joan found positive proof that hypsilophodonts had actually lived in New Zealand. The breakthrough was a small piece of broken bone, later identified as being part of the hip of a 3-metre-long hypsilophodont, probably a dryosaur. Dryosaurs were about the size of a sheep and, like many plant-eating animals, probably lived in small family groups or clans. There is, after all, safety in numbers, especially when you're low down in the food chain and you mistake the sound of distant thunder for the growling stomach of a hungry megalosaur. The problem with identifying New Zealand dinosaurs is that often the only evidence available is a single bone, because over the years huge floods and earthquakes have smashed the skeletons into fragments. But at some locations in the central USA, whole creatures have been found buried intact in stable sediments, which haven't moved since the animals died millions of years ago. So bone fragments from New Zealand can be compared with complete or articulated specimens. At the Museum of the Rockies in Bozeman, Montana, pioneering work done on dinosaur nests by Dr. Jack Horner, advisor on the Jurassic Park films, has provided valuable insights into the parenting behavior of dinosaurs.
The first nest of baby dinosaurs was a nest of little duckbill dinosaurs like this right here. In fact, these are the kinds of the eggs. And basically what we found was some baby bones that were too big to fit in one of these eggs. And yet they were in a nest-like structure. And so we could hypothesize that they had hatched out of their eggs and stayed in their nest for some period of time, at least a period of time that would have been however long it took for a dinosaur to hatch at this size and grow to this size. And so what I hypothesized was that all these dinosaurs had lived in nests because we found them in nests. There was no reason to suggest that they'd left the nest. So if they hatched out of their eggs at, say, a half a meter long, 18 inches long, and doubled in size and still stayed in the nest, then it was most likely that a parent had brought food to them. The reason we know that this is an egg, I mean, you can look at it, you can see it's round, and you can see it's a different color than the rock that it's in, but that still doesn't mean it's an egg. You know, there's lots of round rocks in the world. But what we can do with dinosaur eggs is we just very carefully take some of this eggshell off, and here is some that hasn't been treated. And you take this eggshell, and you take it and put it under a microscope, and you can see pores in it. You can see holes going through it. And then we take it and we make very thin slices through the eggshell and make comparisons, and the eggshell of a dinosaur compares best in structure to the eggshell of an ostrich. It looks identical.
From Dr. Horner's studies, it seems likely that the New Zealand hypsilophodonts nested in small colonies or clans, in a place that was difficult for larger predators to reach. If they behaved like similar dinosaurs in North America, they probably made their nests by scraping up the soil into a conical mound, which they lined with twigs. Egg-laying would probably have started in the spring, once the days became longer and warmer, and, like colonies of ground-nesting birds today, it would have been a relatively short period, with the females laying their eggs within a few days of each other. Possibly 8 to 10 eggs were laid at any one sitting, with the eggs themselves arranged in a circular cluster, with the pointed end sticking down into the soil to prevent them rolling away. But what happened next is open to debate, as Dr. Horner explains.
When it comes to incubating the eggs of dinosaurs, there are two ways they probably did it. Duckbill dinosaurs and probably many probably the hypsilophodonts, probably a lot of other dinosaurs, may have actually covered their eggs with some kind of vegetation, or maybe even in sediment. But derived dinosaurs, the ones that are most closely related to birds, actually sat on their eggs to incubate them, just like birds do. In fact, dinosaurs invented brooding, or this kind of brooding, where you actually sit on it and use body heat. This is one of the reasons that we know that we're very sure that dinosaurs are warm-blooded, because you don't sit on your eggs if you're cold-blooded.
So there's evidence to suggest that hypsilophodonts were good parents, and either sat on their nests to hatch their eggs, or returned to them at the time of hatching to look after the fledglings until they were ready to leave the nest. Despite having put New Zealand on the world's dinosaur map, Joan has never received financial help for her work. But a few years ago, she saved enough money to visit Dr. Jack Horner in Montana. He has a great regard for her work.
Joan's dinosaurs are important because we know a lot of stuff about North America, but we're still learning more. We know a lot about China and Mongolia, but we're still learning more. Australia, New Zealand, we know virtually nothing about. Dinosaurs are very rare there, and the ones that are found are very fragmentary. Really, I think what we need is to get more people out there to look. We need more eyes out there to look.
Joan, for one, is certainly still looking, by comparing her finds with bone specimens from other countries, searching for clues that will prove conclusively where her dinosaurs came from. Joan's guess is that the New Zealand dinosaurs wandered from South America and through Antarctica when New Zealand was still connected to the gigantic supercontinent of Gondwana. In other words, this small group of dinosaurs simply got lost when they were marooned on the New Zealand landmass that broke away from Gondwana 120 million years ago. Of course, it wasn't a process that happened overnight. When New Zealand started to drift away northeast from Australia and Antarctica, the killer asteroid was still 60 million years away in the distant future. And because the climate was temperate and the food supply abundant, the browsing herds of sauropods and the wandering groups of vegetarian ankylosaurs would have been unaffected by becoming marooned. What isn't clear is whether all the New Zealand dinosaurs originally came from South America, for the bones of similar creatures have been found on the Australian continent. The current evidence suggests the New Zealand sauropod bears a closer resemblance to its cousins in Argentina, but the armour-plated ankylosaur is very similar to its Australian relative, the Mimney. Even more intriguing is the fact that these creatures were living in New Zealand at a time when it was still within the polar circle. So these dinosaurs must have spent at least 2 months of the year in total darkness. How did these creatures survive those winter months? To answer that question, we have to leave the rocky southwest coast of New Zealand and travel 1,000 miles across the Tasman Sea to Australia. In the days of the polar dinosaurs, New Zealand was attached to Australia, part of the supercontinent of Gondwana. And recent research by some Australian scientists has provided a better understanding of how the New Zealand dinosaurs might have survived those long winter nights. From the mid-1980s, Dinosaur Cove on the Otway coast of Australia was the site of a grueling 10-year excavation to recover fossil evidence of polar dinosaurs. The team's leader was Dr. Tom Rich, who, in December of 1980, was part of a small band of scientists who found fragments of bone, evidence of dinosaurs that had lived there 100 million years ago. The Otway coast is a wild and inhospitable place. For a start, The bottom of the cliffs where a team would have to work would only be accessible for 5 to 6 hours a day before the tide surged in. But eventually, Tom decided on a promising spot, where it was evident the debris from a swollen river had landed 110 million years ago. So, in 1984, they began to dig into the cliff face. It was tough work, but they were eventually rewarded by the uncovering of some unique hypsilophodont fossils, evidence of polar dinosaurs, which Tom and Pat wrote about in their book, The Dinosaurs of Darkness.
This is an example of the hypsilophodontids, and this is the first one we found at Dinosaur Cove that we knew was a dinosaur. We'd found other dinosaur bones in the Otways, so we knew there were dinosaurs there. And the reason we know that it's a hypsilophodontid is this spike here. The size suggested it was hypsilophodontid, and the spike suggested it was what we call an ornithischian dinosaur, the bird hip dinosaurs to which hypsilophodontids belong.
Over the next few years, the excavation teams recovered a great many fossil bones, but they nearly all came from different types of hypsilophodonts, once the dominant animal in this part of the world. But why? What was it that had given these creatures such a competitive advantage? It would take a lot of work to find the answers, and there was a serious lack of funds. So Tom and his wife sold their house to help pay for food for the volunteers and a living wage for some key field staff. Like Leslie Cool, who has developed an eagle eye for spotting the tiniest of fossils.
Well, that's it right there.
That's it.
I'm glad you do this. Hey. Ah.
So what do these hypsilophodont bones look like when they're buried in rock? How do you know when you've found one?
Well, what we've got here is a hypsilophodont femur. This is the little plant-eating dinosaurs that are most common. And what you can see in this rock is that dark brown circle is a cross-section through the thigh bone or femur of one of these little dinosaurs. And inside it's been filled with mud, which means that one or both ends of the bone are broken for the mud to get in. This is the other half of this same femur. You can see the cross-section through the bone where it's broken. That fits onto the other side here. And then this is the top of the femur here. So the femur ends about here. This is the top of it. It goes into here and then down into the rest of the rock. So that will have to be chipped away to expose the rest of the bone.
Cleaned up, such finds will form part of Pat and Tom's collection of hypsilophodont fossils. Treasures more valuable to them than their house.
And another thing that we have from the sites in the Otways is a little skull. This is the nose end of it, and this is the back end of it. And this is bone along here. And you can see that it's surrounded by rock, and it's been quite a job to get this out of the rock. It's very, very delicate. This is the hole where the eye went. That's what we call the orbit, and it's very large. So these little dinosaurs had really, really large eyes. Now the other thing that's really quite interesting is this gray bit in the back here. The bone's actually been pulled off the top of that skull, and what you're actually seeing there is the inside of the skull that has been filled up with mud, and it's got an impression of what the top of the skull looked like underneath. Those are the cerebral hemispheres there and down here. That's the thinking part of the brain. And back here, these two blobs are the optic lobes. And what our conclusion was that this animal probably could see in the dark. The eyes were big. A lot of the brain was dedicated to processing those signals coming in from the eyes, and it just so happens that this dinosaur lived in the polar regions south of the Antarctic Circle, where for 3 months of the year it was dark.
But being able to see in the dark is one thing. Being active during the winter is another. How do we know these creatures didn't hibernate?
Well, the evidence we have that they were actually active in the winter is sort of analogous to tree rings in a tree. Because when you take a bone like this and you cut it through it and you look at it under a microscope, what you see in most dinosaurs are what we call lines of arrested growth. In other words, where the growth slowed way down. Now, an animal will do that if it's, for example, has a shortage of water or a shortage of food, or it hibernates. If an animal doesn't have those lines of arrested growth, it didn't do any of those things. And so we know it didn't hibernate. Well, these animals didn't, and they all didn't.
If the Australian polar dinosaurs didn't sleep through the winter, it would seem likely that the New Zealand dinosaurs didn't either. And if they didn't hibernate, they might have stood a very good chance of surviving the so-called KT event, the long and terrible winter which froze the planet after the asteroid hit the Earth. 65 million years ago, that killer rock, the size of a mountain, plunged from outer space. It punched through the sky over what is today the Yucatan Peninsula in Mexico, and was so large and moving so fast that any dinosaurs who witnessed the flash of it would have been dead within seconds. It exploded with the force of 100,000 atomic bombs, instantly vaporizing the ocean and gouging a hole 30 kilometers deep into the seafloor. The shock waves rippled around the planet, and billions of tons of dust was hurled up into the stratosphere. Suspended within that dust were particles of iridium from the asteroid, which were deposited to every corner of the planet. Because the element iridium comes from outer space, scientists use its presence to mark the layers of rock and clay set down around the time of the impact. It's called the KT boundary. That boundary also marks the point of mass extinction, 65 million years ago, when not only the dinosaurs, but 70% of all animal species were wiped off the planet. There have been several mass extinction events in the history of the planet. 300 million years ago, it was the age of the fishes. Then the dinosaurs ruled for 140 million years before the KT event killed them off and allowed the mammals to take over. But these divisions cover a period of 600 million years. So, within the age of the dinosaurs, paleontologists have defined three major time periods: the Triassic, the Jurassic, and the Cretaceous. As it happens, the New Zealand dinosaurs Joan Wiffen found all lived in the late Cretaceous period, which ended with the asteroid impact which marked the KT boundary. But the fact that these dinosaurs also lived half a world away makes them very valuable. Because if we could discover what killed the dinosaurs in New Zealand, we'd have a vital clue to solving the puzzle of why they became extinct worldwide. Dr. Vivi Vajda is a Swedish scientist who studies fossilized pollen. Recently, she wrote a paper with two New Zealand scientists which claims that shortly after the KT event, nearly all the plants in New Zealand vanished, except for the ferns. Her method involved collecting samples of rock by chipping above and below the KT boundary line at selected New Zealand locations. These small rock samples containing the fossilized fern spores were carefully bagged and labeled in the field for later analysis. Back in Sweden, in her laboratory at the University of Lund, Vivi set about the meticulous process of extracting the pollen samples by first dissolving the rock in acid. Before preparing the delicate slides for examination under the microscope. Then it was simply a matter of laboriously counting and recording the various kinds of pollen spores in each sample. What she saw absolutely amazed her.
I couldn't believe my eyes. What I discovered in the microscope was that the samples below the boundary contain a rich flora with flowering plants, gymnosperms like podocarps, and also ferns. After this catastrophe, you find really not anything else than fern spores. And those were the first plants to recolonize the earth after the devastation. So first came the ground ferns, which were well adapted to this cold and darkness. And after those came the tree ferns, when it started to get a bit warmer.
So the New Zealand plant history shows that the effect of the asteroid hitting the planet was truly worldwide. Those creatures near to the impact, of course, died instantly. But how did it affect the dinosaurs living in faraway New Zealand? If the prolonged winter caused by the dust in the atmosphere didn't kill them, what did? Wildfires, perhaps triggered by lightning, raged through the forests, completely destroying the plant life. Those dinosaurs that did not die in the inferno eventually died from lack of food.
So what we can tell from the changes in the plant record is that there wasn't enough food for the dinosaurs, so the plant eaters starved to death. And of course soon after the carnivores died. And that means that this meteorite impact had a global effect on the life.
At least that's our best guess to date. Joan Wiffen earned an honorary PhD for proving that dinosaurs did once live in New Zealand. But exactly why they were lost remains unproven. If the polar dinosaurs were able to survive the wildfires and find enough food, then we may still be in the dark about why these dinosaurs died in the winter that followed the KT event.
What these polar dinosaurs say about the KT event is it couldn't have been just a short, brief nuclear winter type phenomenon. It wasn't just 2 or 3 months of turning out the lights, because these animals here were getting through that sort of event every year. And so it's unlikely you would have wiped them all out. I mean, what is very interesting about the KT boundary when you start to think about it is, think of every animal and plant around you. They all had ancestors that got through it. Why did the non-avian dinosaurs all drop out? We have birds, which are dinosaurs, left. But the ones we think of as dinosaurs in the conventional manner, the non-avian dinosaurs, all went, and they went together, and we don't know why. But what we can say from this stuff is that it wasn't just from getting a cold snap that was a brief period. It had to be something else. That's the contribution this makes to that argument.
And there surely must be a something else. An X factor which explains why so many of the marine reptiles also died out. Why did the crocodiles survive? And the avian dinosaurs become birds, whilst other creatures came to the end of the line. Was there something in the cold-bloodedness of crocodiles that gave them the competitive edge over bigger and more dangerous warm-blooded predators? For why should the crocodile manage to survive, and the mosasaurs, arguably the top ocean predators of all time, all die out? The riddle of why so many sea creatures vanished has yet to be solved. For the mosasaur did not disappear alone. Its fellow predators, the long-necked elasmosaur and the flying pterosaur, also disappeared. Did something happen to the fish supply? Or were these creatures simply more sensitive to the changes in the overall environment after the asteroid struck? And what of the land animals? We know now that the polar dinosaurs didn't hibernate and survive the long winter after the asteroid impact because they were warm-blooded. Or do we?
Were the dinosaurs that lived in New Zealand warm-blooded or cold-blooded is a mystery that I'm not certain what we can solve. There is some evidence that the small carnivorous dinosaurs may have had feathers. And certainly new discoveries in China would suggest that. If they had feathers, then maybe they were warm-blooded. There's been some studies done on the bone structure, which also would seem to suggest that they were warm-blooded. What about the dinosaurs in New Zealand? That's a tough one because we don't have the evidence for feathers or other body structures. It's a very good possibility that at least some of the small meat-eaters were warm-blooded. But all of them, we just don't know right now.
Dr. Joan Wiffen is encouraging the next generation of paleontologists to remain curious about dinosaurs. After all, they did rule the planet for 140 million years. And if they became extinct, might we also one day disappear? Joan is living proof that everyone can contribute to science. Like her, we need to keep chipping away at the past. For our future may confront us in the very next turn of a rock.